Rapid Spanning Tree Protocol, or RSTP. This powerful Layer 2 protocol addresses all the limitations of traditional Spanning Tree Protocol, or STP, by allowing switching networks to reconverge in a rapid amount of time. But what makes RSTP so different to STP, and why does it work so much more quickly? These questions plus more will all be answered in this video. Hey everybody, and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this video, what I'm going to be going through is RSTP, or Rapid Spanning Tree Protocol. Now, if you don't know what STP is, or Spanning Tree Protocol, please check out this link. It's a video that I've done that explains all the building blocks of STP, and you really need that before going any further. But essentially, RSTP allows a network to reconverge in, guess what, a lot quicker period of time. It's rapid. That's what the R in RSTP actually stands for. And when you compare that to STP, when there was a topology change, such as a port going down, a switch going down, or a new root bridge election, whatever it may be, typically you would have at least 50 seconds of that network reconverging. And that was fine for when STP came out many years ago. But networks have changed since then, and they've changed drastically. They've changed dramatically. And in today's modern networks, we need network uptime all the time, don't we? We don't want our networks to be spending even a second to reconverge, even at layer 2. And that is where RSTP comes into it, because it allows that rapid reconvergence. And in this video, what I'm going to be going through is, how does RSTP compare to STP? What are the similarities? But also, what makes RSTP different? i.e., what does it bring that's new that STP doesn't have? And essentially, how does it have this rapid reconvergence? And this comes down to what's called in the RSTP world the sync mechanism. And that is essentially where you've got one switch sending out a proposal BPDU, or Bridge Protocol Data Unit, and the other switch sending out an acknowledgement BPDU, and it just allows that network to reconverge a lot quicker. And I'll go through a few illustrations of how that actually works. But there's no configurations, there's no lab in this video. We're starting, as always, with the theory and building up from there. But for now, let's just go straight into that theory and learn what is RSTP, how does it compare to STP, and then build up to that sync mechanism from there. Okay, so let's start off with the theory. Let's start off with the similarities between STP and RSTP. I'm not going to go through all the similarities, but I'll try and mention them all along the way. But let's just start off with the obvious ones. First off, as it says here, the fundamentals of STP is exactly the same for RSTP. So there has got to be one root bridge, wherever you've got 3 switches, 4 switches, 5 switches, all connected together in this nice big looped topology. There's always got to be that one root bridge. And that one root bridge is basically sending out in the STP world those topology changes, and all switches send up to that root bridge out of their root port those topology change notifications. So there's always got to be a root bridge, and we have that in the RSTP world. And as it says here, each non-root bridge, so a switch that is not a bridge, a root bridge, it has got to have one root port. That root port is basically the lowest or best cost for that switch to get back to that root bridge. So in the RSTP world, there's still this concept of not RSTP, but of a root port. And in RSTP, there's still this concept of a designated port. So a designated port is the port that's facing away from the root bridge. So on a root bridge, you would have designated ports because they're facing downlink. On non-root bridges, you would have designated ports that face a particular LAN segment, i.e. not facing the root bridge. And the SDP tuning process in terms of electing that root bridge is exactly the same. So what I've done here is I've just put in two switches, SW1 and SW2, and the election process is exactly the same in the RSTP world as it is in the STP world. So first, initially they look at the bridge identifier, which is made up of the priority and the MAC address of the switch, of the chassis. And as we know, lower the cost is more preferred. And that is exactly the same in terms of RSTP and STP. The root bridge will be elected based on lower, i.e. the more preferred bridge identifier, and if there's a tie, they then look at port cost and port priority. That is exactly the same. Nothing has changed there. But of course there are some differences. First one, and I'm going to go through it just now, are port costs. So there is a new way of configuring the port costs to get back to that root bridge, or choosing which ports will be designated and blocking or discarding in the STP world. There are also some new port states and some new port rows. We'll go into those in just a minute's time. And as I said, there's also this concept of state transitions, i.e. a sync message, which allows, if these two were running RSTP, and I know this isn't really a looped network, of course, but if these were running RSTP, it would allow them to converge a lot more quickly. But what is this port costs? Well, this is where RSTP really starts to differentiate itself a lot more quickly. So when we were using traditional spanning tree protocol, it was using a 16-bit value to identify that port cost to get back to the root bridge. But with RSTP, it's using a 32-bit. So the 16-bit was what's known as a short cost, and the 32-bit is what's known as a long cost. And it's also important to note that the newer switches that you see, regardless of vendor, typically they go for the long cost value. In older switches, you might still see the short cost values, but just be aware of that in the RSTP world you can configure long cost values. But what do these actually look like? And this is what they actually look like here. And really, when we look at port costs, it was to accommodate faster speeds, faster links. When you looked at STP, and you can configure RSTP to use the short costs. When you look at STP and this short cost value, you've got 10 megabits per second, which would have a cost of 100 megabits per second, which would have a cost of 19, 1 gigabits per second, cost of 4, 10 gigabits per second, cost of 2. But for 100 gigabits, 1 terabits, and 10 terabits per second, you could see here they were completely blank. It was just not applicable. The short cost, the 16-bit value, so all of this here was defined in that 16-bit header, didn't really define any costs for anything that went above 10 gig. Whereas with the long cost value, because this has a 32-bit value, you can see that the costs are obviously a lot bigger because there's more room to play with. And now we can actually accommodate from 10 gigabits up. Now, really, are you going to be having 10 terabits per second in an access network at layer 2? Honestly, I don't know. It's not for me to say, and you can see it's got a cost of 2 there. But the RSTP protocol, which is defined in the 802.1w standard, does allow for that, and therefore it becomes future-proof. Will we ever see 10 terabits or even 1 terabits per second at the access layer? I don't know. Honestly, I don't know. But again, the standard allows for it. So that is just immediately how RSTP is different to STP, as it brings into the network and into layer 2 this concept of port costs, i.e. this 32-bit long cost value, whereas everything else is pretty much the same. But of course there's more to RSTP. And I just said on the last slide that there are some differences in the RSTP port states. Now with STP, what the standard has is blocking, listening, learning, and forwarding. So blocking being it's just not doing anything over that interface for that particular collision domain. It's blocking any frames that are coming in. It's listening to BPDUs from the switch on the other side of the link, but it's not doing anything with it. Listening is a transitive state where you are with a switch, the switch is listening on the wire on the interface to all those BPDUs coming in, but not doing any MAC learning. Learning, another transitive state, is where we are learning, the switch is learning those MAC addresses, and forwarding is a stable state where it's forwarding frames, it's forwarding BPDUs. So we've got 4 under STP port state, but in the RSTP world, whilst there still is learning and forwarding, the discarding state really combines the blocking and listening into one single state. So in the RSTP world, there is 3 states. In the STP world, there are 4 states. And it's also important to note that when in the STP world, when you enable a port, when you configure a port to run STP, it immediately transitions to the listening state. Whereas in the STP world, when you configure an interface, a port to participate in RSTP, it will immediately come into the discarding state. And that is because the discarding state, that port state, it combines blocking and listening into one. And if you know STP, you know that when it moves from a blocking to a forwarding state, i.e. it's blocking traffic to forwarding traffic, it's got to transition through the listening and learning states. That's why listening and learning are transitive states. They're not stable states, they're states that the interface needs to move through. And when a port is enabled or there's a topology change and that port is moving away from blocking to forwarding, it's got to move from blocking through listening, where here it will spend 15 seconds. Let me write that somewhere else. So it spend 15 seconds here in the listening state, and then it would move down to the learning state, where again it will spend another 15 seconds, and that is because of that forward delay timer, before it actually then moves on to the forwarding state. So immediately there you've got 30 seconds just wasted really on the transitive states that you get in the STP world. And what RSTP brings to the table that is new, and I'm going to do more and cover more about these new ports on the next slide, is that they bring in these new ports, the alternate port and the backup ports. Again, I'll come on to more information into these in just a minute's time. But for now, just know that these are stable. These type of ports are stable when they are discarding. So they're not actually forwarding any network traffic. They are right here in this discarding state, and that's where they should actually remain. Whereas when we look at root and designated ports, they can actually move, they can transition from discarding immediately to the forwarding state, where they should absolutely be stable. And you might be wondering, well, why is this learning state actually here in the RSTP world when a root or designated port can just immediately go into the forwarding state? Well, if the sync process fails, more information to come on this sync mechanism in this video, this would then prevent that port moving immediately from discarding to forwarding, so moving from here over to there, and therefore that switch has to go through that learning stage just like it would do in the STP world. Why would the sync mechanism fail? Well, basically RSTP is backwards compatible with STP, so RSTP can work with STP, but STP doesn't support this sync mechanism here, and thus if RSTP is trying to speak to an STP switch, it needs to revert back to STP. So that's why there is this learning state here in the STP world, in the RSTP world, sorry. It's getting a bit confusing between STP and RSTP, these different acronyms, but you know what I mean. And in the RSTP world, when you enable a configuration on an interface, yes, it's going to be in the discarding state here, but it will also be a designated row. So all interfaces in the RSTP world will initially be designated. But if the RSTP algorithm, the learning process, determines that the port is going to be an alternate or backup port, more information in a few minutes, then it will remain in the discarding state, because don't forget, these alternate and backup ports, they will be stable in that discarding state. And just to bring more illustration, more information back to what I was just saying, if that sync mechanism succeeds here, that switch can transition from discarding to forwarding absolutely immediately. No questions asked. But if the RSTP sync process fails because RSTP, you've got a switch that's communicating over a link with a switch that only supports STP, the sync mechanism is going to fail because STP doesn't have this concept of a sync mechanism, and then that RSTP speaking switch has got to spend a certain amount of time in the discarding state and 15 seconds in the learning state before it then eventually gets into the forwarding. So it's going to spend 15 seconds here and another 15 seconds here, and thus it's basically the same learning period that you get in the STP world, i.e. 30 seconds in total. So yes, RSTP is backwards compatible with STP, but RSTP should be really that preference, that protocol of choice in a layer 2 network to prevent loops, because as you can see, it could just get into a forwarding state a lot more quicker because of that glorious sync mechanism. So let's now discuss those new RSTP port rows that RSTP brings, and I've already mentioned them, the alternate and the backup port. But just as a quick recap, the root ports, they are pointing towards that root bridge. They have the lowest cost to get back to that root bridge, whoever that root bridge actually may be. And there should only be one root port on a particular switch for that VLAN. The designated ports, they point away from the root bridge. They're pointing downlink. They're pointing away from the root bridge for a particular LAN segment. And here is this alternate and backup port. But you might be reading that there's this new thing called a non-designated bridge. A non-designated bridge is a new term in the RSTP world. It is basically that non-root bridge, that switch which has designated interfaces facing away from that root bridge. And as such, it's going to have two different rows. It's going to have an alternate port and a backup port. The alternate is quite literally, if that root port fails, if the transceiver goes down or if the port is just disabled, whatever it may be, the alternate will just kick into effect and become that root port back to that root bridge. The backup port is when you've got a hub, basically. So this is going to be very rare. I'd be surprised if you see this today. But a backup port is if that designated port fails. So that non-root bridge, that non-designated bridge, it would have an alternate port back to the root bridge if the root port fails. But also if it was connected to two or more other switches via a hub, it would have a designated port connecting into the hub, but it would also have a backup port if that designated port fails. And that port decision in terms of electing which port is going to be root, designated, alternate and backup, it's still exactly the same. So in terms of the root port, it's going to be the lowest path back to that root bridge. If there's a tie, so if there's two interfaces that have the same cost on the same switch to get back to that root bridge, it's going to look at, well, what's the lowest bridge identifier, and then it's going to then look at what's the lowest port ID as well. And I thought I'd include this illustration just to talk through what I've been discussing so far. And let's just say, for example, upstream connected to SW1 is another switch, and that is that root bridge, just for example. And this will then allow SW1 and SW2 to determine what ports are in which particular port rows. And it does so based on this. What is the lowest path cost to get back to that root bridge? If there's a tie, it will then move to the second part where what is the lowest bridge identifier. So maybe there's different routes to get to that same root bridge. And thirdly, what is the lowest port ID? That's the third option to break that tie. So we know on SW1 it's connected to that root bridge. So right here is going to have a root port. Now downstream from SW1, it is going to have a designated port, but it's also going to have a backup port, isn't it? Because it needs to have, in the RSTP world, a backup port when there is a hub, and you can see there's a hub right here. So the question then is, well, what port will be the designated port and what port will be the backup port? Well, the answer is what is the lowest path back to the root bridge? That's not applicable here. What is the lowest bridge identifier? They're both on SW1. So what is the lowest port ID? It's gig01. So this then becomes the designated port, and this would become the backup here. From SW2's perspective, it will look at, well, I can get to the root bridge via the hub through SW1, but let's say over the gig01 it has a cost of 4, and gig02 it also has a cost of 4. Well, that then breaks, it doesn't break it, that then moves away from the first part because the lowest path both has a cost of 4. So then it will look at, well, what's the second option? What is the lowest bridge identifier? Well, SW1 is the same bridge, so it then moves on to the third option. What is the lowest port ID? Lowest port ID is gig01. So now this would become the root port, and this would become the alternate port. And thus, if gig01 fails, and this just moves into a completely discarding state, this would then transition into the root port as well. But in summary, in the STP world, we had the root port, we had the designated port, and you also had the disabled port, which is basically where an interface isn't configured to take part in STP. But in RSTP, it brings to the table the alternate port row as well as the backup port row, and it also still has the root port. You've got to have that, and the designated port, and of course the disabled port row as well. So let's now go through the algorithm, but in a bit more detail in terms of using RSTP. Now, as I said, that tuning process to get this loop-free topology, it is the same as in the STP world. RSTP is using that same algorithm to get that loop-free topology. And there's 3 main steps. 1, get that root bridge. 2, get the root port. 3, elect your designated ports, and then anything else is alternate or backup. So if we just use the quick topology here, which one will be that root bridge? Well, we know it's going to be SW1 because it's got the lowest bridge identifier with a priority of 1 here. If you look at all the other bridge identifiers, they all have a significantly higher priority, and thus this bridge here, SW1, will become the root bridge. The second part is to elect the root port. Now, from SW2's perspective, which one will be the root port, i.e. to get back the best cost to get back to the root bridge? If you said or thought it would be this link here, you would be wrong, because that is a fast Ethernet. Everything else is a gig. So this fast Ethernet, even though it's a direct connection back to the root bridge, it is a higher cost. So this would actually be a discarding row. So it's not going to be forwarding traffic. That's just going to break the loop. But which ones would be the root ports on the other switches? Well, first, it then comes down into this decision-making process here, i.e. what has the lowest root cost on those different interfaces? What is the lowest neighbor bridge identifier? If there's a tie, what is the lowest neighbor port ID? If there's a tie there, what is the lowest local port ID? And that then should break it. So if we come back to SW2, we've got gig01 here and gig00 here. Really, they're connected to SW4, which is going to have that same root cost to get there, and it's going to have the same neighbor bridge identifier. So which one would then become the root port? It would be gig 00, so this would be the root port because gig 00 is connected to gig 02, and that is lower than gig 03. And then the gig 01 port, this will become the alternate port to really serve as a backup, without confusing terms, an alternate port if that root port should fail. On SW4, what one would be the root port? Would it be gig 00 or will it be gig 001? Well, the answer is what is the lowest root cost. So say they've got the same root cost. What is the lowest neighbor bridge identifier? They're both connected to the same switch, bridge or switch 3. What is the lowest neighbor port ID? Well, really, we've got this hub in the middle. We didn't have that here, did we? So that's not really going to work here because both interfaces are going to see both gig 02 and gig 03. So then it looks at what's the lowest local port ID. That is obviously gig 00. So then this becomes the root port and this becomes the alternate port. And finally on SW3, same concept as we just went through. The gig 0 port will become root port because it's the lowest ID, and then gig 01 will become the alternate port. And then once you've got your root ports, then have the designated port selection. So on SW1 here, this is going to become a designated port. The F02 will become a designated port, but which one will become gig 00 or gig 01? Which of those will become a designated port? It will be gig 00 because it is lowest port ID, and this would then become a backup interface. On SW3, which one would become the designated port? It would be gig 02 because it's the lowest port ID, and here you would then have your backup port once again. And then finally on these two interfaces here, which one would be designated? It would be gig 02 because it's the lowest port ID, and gig 03 would become that backup. I know that got a bit messy there, but that's just how the algorithm works, and it does so in such a quick way. But what RSTP also introduces, which is new, is this concept of link types. And really the link type does dictate whether that sync mechanism, which I'm going to go through next, whether that sync mechanism can actually work or not. So if you've got a point-to-point like you've got between SW1 and SW2, so this would be a point-to-point connection, this is going to allow that sync process, that sync mechanism to actually work, and thus those interfaces can move straight from a discarding straight and immediately into forwarding without going through that learning state. But this is where you've got point-to-point and full duplex, and that is just configured by default. But there's also these other two link types such as shared and edge. So edge is really when you connect into those end users, ourselves with our terminals or servers, whatever they may be. My drawing is all really bad, but obviously in such a scenario you can't use that RSTP sync process because these servers here, they're not really network devices. Yes, they connect to the network, but they're not participating in the RSTP selection process, and therefore this is really going to be running without the RSTP sync process, and you're not going to be able to transition those interfaces straight into a forwarding state. And the same for shared, but these do not connect to end devices like servers and workstations, but instead connect to other devices, other networking devices like the interface here, but you've got this shared medium like a hub in the middle, and therefore again you cannot use the RSTP sync process. So just know in RSTP, unlike STP where everything is pretty much point to point, but there's no sync mechanism in STP, in RSTP you can use the sync mechanism, but it's only when you've got this point-to-point configuration, full duplex, and then that sync mechanism can be utilized to get that network reconvergence done a lot more quickly. And that is also assuming that SW2 and SW1 both run RSTP. If SW1 only ran STP and SW2 ran RSTP, then obviously the sync mechanism is again not going to work, and STP being backwards compatible to STP would actually run STP instead of RSTP. So let's build up to that RSTP sync mechanism. But to understand how that sync mechanism works, we just want to take things back and look at the STP convergence, i.e. what happens when an STP network is first initialized and span up, the interfaces are participating in STP. What's the process? Well, in the STP world, when a port is first enabled, what all those interfaces will do is they will go into the designated row. And in the designated row, what is happening is that both ports, in this case gig 01 on both switches, they're going to be listening over here, and they're going to have the row of designated as well, because at this point both switches believe that they are the root bridge, and thus they're listening on the wire for any BPDUs that may be out there. And of course there are bridge protocol data units or BPDUs out there, because as I just said, upon first initialization, switch 2 and switch 1, they both believe they are the root bridge. And so therefore SW2 is going to be sending out its BPDUs, and switch W1 are going to be sending out its BPDUs to say, hi, I'm the root bridge, I'm the root bridge. And they almost need to agree on who the actual root bridge is. And this is the whole process. It's the first initial step, don't forget, in the STP algorithm, is electing the root bridge. And what happens here is that the switch is basically listening for any superior bridge protocol data units from another switch. So when the BPDU is received over the wire from SW1 on SW2's interface, it will see the bridge identifier of SW1. And at this point, SW2 knows that it's inferior, because it knows its bridge identifier starts with a priority of 4096, but the bridge identifier on SW1 starts with 0, so it's lower, it's absolutely more preferred, it's inferior. And so it knows that SW1 is at this point going to be the root bridge. And when SW2 knows that SW1 is that root bridge, it then immediately moves its gig 01 interface into a root port. It's still listening on both ends of the link, but the interface on SW2 is now that of a root port, because it's the lowest cost to get back to that root bridge, i.e. back to SW1. And it also stops sending any BPDUs. We don't send, in STP, you don't send BPDUs out of your root port, unless there is of course a topology change. But for initial first boot up and start of the STP process, at this point there would be no more BPDUs being sent out of that root port. But obviously the network hasn't converged yet, and both switches, their states on the interface were in the listening state right about here, but now they've transitioned into the learning state. So we've moved from the listening state into the learning state. We were in the listening state for 15 seconds. So for 15 seconds, SW1 and SW2, they were listening for all those BPDUs that were coming through on the links, learning which BPDUs were superior, if any, which BPDUs were inferior. And after the 15 seconds, they then move into this learning state, where those switches, those interfaces, are learning the entries, learning MAC addresses that are communicating. And it doesn't stop there with classic STP. After another 15 seconds, so after another 4 delay timer has expired, those interfaces will then move into that final state where they need to be, into that forwarding state where they can actually forward traffic, forward layer 2 traffic back and forth. So yeah, both switches at this point can send those data frames between SW1 and SW2, but every 2 seconds the root bridge SW1, it will send out those hello BPDUs just to reassure SW2 and any other switches that, hey, I'm still here, I'm still here, I'm still here. There's no configuration change, there's no topology change. Just keep running as you are. This is how generally the classic STP convergence works. How is this different to RSTP? Well, with the RSTP convergence, when those same switches, when those same interfaces are just configured and booted up to take place in RSTP, just like before, they're going to go into the designated rows. So gig 01 on SW2 will become designated, and gig 01 on SW1 will become a designated row as well. But what is different compared to STP is that they will both be discarding. Don't forget that the discarding state in RSTP is the blocking and learning states combined in RSTP. It's just called discarding. But this is where RSTP now starts to differ because of this sync mechanism. So yeah, just like in STP, SW1 is going to send out its BPDU and SW2 is going to send out its BPDU. But the big difference is that inside those bridge protocol data units, that proposal bit, a proposal bit, is going to be sent out in that BPDU by both switch 1 and switch 2. And what the proposal bit is basically doing is both switch 1 and switch 2, they're saying, I'm proposing to you, to switch W2 or to SW1, depending which way you look at it, that I have that designated port for this LAN segment. So if SW1 is sending out this proposal BPDU, it's saying, over this link here, I have the designated port. But at the same time, SW2 is sending over its proposal bit saying, I have the designated port for this LAN segment as well. But it all comes back to this, is which is superior to begin with. And just as before, SW1 has a superior BPDU because of its bridge identifier. It has a better priority of 0 compared to the priority on SW2. And when SW2 received that proposal BPDU from SW1 and learned that its priority was superior, that it was the root bridge, what it's going to do now is two things. One, it is first going to send an agreement BPDU back to SW1. It's going to say, okay, I agree that you have the designated port for this LAN segment, for this collision domain. And what it will also do is it will move the gig 01, the row, away from designated to being a root port, because it knows with no other links obviously here that it has the best and lowest cost to get back to the root bridge, i.e. SW1. And almost immediately after, the state on the gig 01 on SW2 becomes forwarding because it sent out the agreement BPDU. It said, I am agreeing to you, SW1, that you are superior to me. And once SW1 has received SW2's agreement BPDU, it can then move its state into forwarding as well. This is basically the sync mechanism. It's syncing the devices together and using that proposal and agreement bit in the flags field in RSTP to agree who has that designated port for a particular LAN segment, and that is purely based on initially on the bridge identifier. And all of this happens in less than a second. So compare that to STP. This is extremely fast and a lot quicker than that 50 seconds at least that you get with STP. But of course the last illustration was quite straightforward. There was only two switches. What happens when there's more than two, i.e. three switches, as you can see here? Was just as before, switch W1 is that root bridge. It has the best priority. Both switch 2 and switch 3 have the same priority, but really SW1 is that root bridge. But how does it change? Does it change at all? There is a slight change, but it's really not significant, and this will just be rolled out across the network. It will just happen automatically for you when running RSTP. So just like before, SW1 will send out a proposal BPDU. At the same time, SW2 is also sending out its proposal BPDU. But when SW2 receives SW1's bridge protocol data unit and sees that it's superior because of its bridge identifier, because of its priority, it is then going to move all non-edge interfaces, i.e. interfaces that are connected to another switch, another networking device that are not edge. It is going to move them into a discarding state, just to allow for this sync mechanism to actually take place. And just as before, once it's received that superior BPDU and moved that interface from designated to root, it will send the agreement bridge protocol data unit, the BPDU, back to the root bridge, back to SW1, switch to remove that interface into forwarding, and when SW1 receives that agreement BPDU, it also moves that gig01 interface into forwarding as well. So just like before, as we just went through, this is the same minus the other interface connecting to SW3. For now, that is discarding, but the link between SW1 and SW2, for all purposes, is up and running in terms of RSTP. They're forwarding traffic, but now we need to enable that link. RSTP needs to enable that link between SW2 and SW3. And so at this part, really the same process takes place. SW2 will send out its proposal BPDU to SW3. SW3 will send back to SW2 its proposal BPDU. And at the end of the day, SW3 will learn that SW2's BPDU is superior because it is connected to the root bridge. It's connected to SW1. The cost by default is going to be better. So then it sends out, SW3 sends out its agreement BPDU back to SW2 saying, yeah, okay, I agree that you have that designated port for this LAN segment, for this connection between us. I'm going to move my interface into a root port. You can have your interface as a designated port. And when SW2 receives that agreement back from SW3, it will then also move its interface into a forwarding state. And this happens time after time after time, link by link, switch by switch. So all of this in less than a second. So it's very fast, it's very rapid, and that's where the R in RSTP obviously comes from. But this is the sync mechanism. This has a lot of benefits over traditional STP, as I'm sure you can see. But don't forget, the sync mechanism only works on switches which are running RSTP on both ends. You can't have one switch running RSTP and another switch running STP and expect to get the rapid convergence that you get in RSTP. That won't happen because that STP speaking switch can only speak STP. RSTP is backwards compatible to STP, but you lose the sync mechanism, i.e. you lose the ability to have fast convergence because STP just doesn't understand RSTP. And so that's it, everybody. That's the end of this video. That's the end of this part into STP, really into RSTP. Really, if you know STP, it's not that difficult to go from STP to RSTP because you've got the building blocks in STP. You know what a root port is and a designated port and how that election process takes place, and hopefully what a BPDU looks like in the STP world. RSTP just adds in that rapid convergence, and it adds it in by having that sync mechanism, by having those proposal BPDUs just exchanged initially between switches, and then when they agree who's superior, sending the agreement back and both ports going into forwarding. And if you're connected to other devices, if a switch is connected to other switches, obviously discarding on those interfaces and then rolling that proposal and agreement procedure out throughout the network in less than a second. So very fast, very capable. But also RSTP does have these new additions on top of STP, such as those port rows, the alternate and the backup ports. I don't think you're going to see a lot of backup ports these days because hubs typically, I've not seen a hub in quite a few years, but the RSTP does bring in those additional ports, as well as those different port states. In STP, the port states is you've got blocking, then you've got listening, learning, and forwarding. So 4, whereas in the RSTP, there's only 3, where you've got discarding, learning, and forwarding. And with RSTP, you can just transition straight from discarding into forwarding because of that sync mechanism. But I hope you found that useful, hope you found that informative. If you like my content, please give me a thumbs up. It's the best way to support my channel. Any questions or comments, let me know down in the comments box. Other than that, thanks for watching and goodbye.